Hey there guys, welcome to my walkthrough of the 2018 OCR MEI New Specification A-Level Maths Paper 3, which is Pure Mathematics and Comprehension. So, each question is in its own video. You can get to the playlist from the description, and I'll pin it as the top comment. Also, in the description are the Paper 2 and Paper 1 walkthroughs, as well as the website to get the papers and my A-level content. Okay, if you're finding these useful, please give us a thumbs up, get subscribed, be awesome, let's go. Okay, now for section B, I'm going to do this all in one go. It's the comprehension section, 15 marks, so you can get the insert, which is this exciting thing. You can get this from their website. It's a good idea to have a read through before attacking the questions. I'll put it on screen when we need it. Again, you can get it down below from their website, which is linked. So, question 11, it says, line 8 states that a plus b over 2 is greater than or equal to root ab. For a and b greater than or equal to 0. Explain why the result cannot be extended to apply in each of the following cases. So, part 1. One of the numbers a and b is positive and the other is negative. So, in part 1, in this case, a times b is negative, and so root ab is not a real number. You can't square root a negative number unless you're doing further maths and we use imaginary numbers. Part 2. Both numbers a and b are negative. Okay, so in this case, AB is positive, so root AB is real, but a plus b over 2 is negative. So, in this case, a plus b over 2 would be negative, so less than root a b. Cool. Okay, question 12. Lines 5 and 6 outline the stages in a proof that a plus b over 2 is greater than or equal to root ab. Starting from a minus b squared is greater than or equal to 0, give a detailed proof of the inequality of arithmetic and geometric means. So, if you've read through the insert, you know the arithmetic mean is a plus b over 2, and the geometric mean is root ab. Okay, So we need to then basically turn a minus b squared is greater than or equal to 0 into a plus b over 2 is greater than or equal to root a b. So it's not a particularly obvious proof. I've seen it pop up in other papers. So let's start by saying then, given that a minus b squared is greater than or equal to 0, let's expand the brackets. We get a squared minus 2ab and b squared is greater than or equal to 0. Now if we add the 2ab, let's add 2ab, so we get a squared add b squared is greater than or equal to 2ab. Now on the left we know that we just want to end up with a plus b up on top, and on the right we're going to have a square root of a b. So what we need to do here is think about how we could factorize the left hand side to give us a plus b inside of a bracket. So we could think of a squared plus b squared as a squared add 2ab add b squared minus 2ab. Then the 2ab minus 2ab cancel out, but we can factorize a squared add 2ab add b squared to a add b all squared. So that's greater than or equal to 2ab. If we then factorize on the left, we get a plus b squared minus the 2ab is greater than or equal to 2ab. Add 2ab to both sides, a add b squared is greater than or equal to 4ab. Square root both sides, a add b is greater than or equal to a root 4ab. A add b is greater than or equal to root 4 root ab, so that's 2 root ab, and then finally divide through by 2 and we get a add b over 2 is greater than or equal to root ab. QED, quite enough done. Okay, question 13 for 3 marks answers 2. Consider a geometric sequence in which all the terms are positive real numbers. Show that for any 3 consecutive terms of the sequence, the middle term is the geometric mean of the other 2. Okay, so in my geometric sequence, I'm going to let the first term be x, and the common ratio can be y. and then my three terms are x, x, y, x, y squared. Now the insert tells us the geometric mean. So the geometric mean of x and x, y squared is square root of x times x, y squared, which is the square root of x squared, y squared, which is root, sorry, no it's not, it's just the square root of x squared, y squared, it's just x, y, which is the middle term. Boom. Question 14. In Fig C1.3, angle CBD is equal to theta. We want to show that angle CDA is also theta as given in line 23. So, angle CDA is this chap here. So this is the angle that we need to find. So, we are in a semicircle, and we know that this angle here is a right angle. Now we also know that when chords come off of the ends of a diameter and meet on the circumference, they do so at 90 degrees. So we know this whole angle up here is 90 degrees. Now if we call this angle x, then we know that x add 90 add theta is equal to 180. So that's just adding all the angles in the big triangle A, B, D. So that can tell us then that x is 90 minus theta. So then we know that angle CDA, so let's call it y. We then know that y add 90 add 90 minus theta is equal to 180. So now we are summing the angles in the left-hand triangle. So y add 180 minus theta is equal to 180. Take 180 from both sides. Y minus theta is 0. Y is theta. Boom. Okay, then part 2 wants us to prove that h is a root AB as given in line 24. So, this now comes down to SOC2. So we now have two angles that are the same. Now it turns out that for both of these angles we know the opposite and the adjacent. So from the left hand side we can get that tan theta is equal to the opposite A over the adjacent H. From the right hand triangle we can get that tan theta is equal to the opposite H over the adjacent B. Now both of these are tan theta, so that means they are both equal to each other. So from that we can say that H over B is equal to A over H. If we multiply through by H, we get H squared over B is equal to A multiplied through by B, H squared is A, B, and then finally H is root A, B. Boom. Okay, number 15, the final question, a proof by contradiction for 3 marks. So, I do think this is quite a tricky one to get your head around, so I'm going to try and go through it as simply as possible. So, it is given in lines 31 and 32, and that the square has the smallest perimeter of all rectangles with the same area. So think about what that means. That means that for any lengths of a rectangle with the same area, the perimeter is smallest when all 4 sides are the same. Using this fact, prove by contradiction that among rectangles of a given perimeter for L, the square with side length of L has the largest area. Okay, so the first step with proof by contradiction is to assume the opposite of what we are trying to prove, and then see what trouble that gets us into. So we are going to assume there is a rectangle with perimeter for L that has a greater area than the square with perimeter for L. Now, let's think about then what that means. If there is a rectangle with the same perimeter as the square but a greater area, that means then that there has to exist a square with the same area but a smaller perimeter. It's not allowed to be bigger. So that then means there has to be a square with equal area but a perimeter less than 4L, because we're not allowed to increase the side lengths. So has equal area but a perimeter less than 4L. So side length is less than L. So let's think about what we're saying at this point. We are saying there is a square with the same area as this rectangle but a perimeter less than 4L. So same area, smaller perimeter. That seems a bit fishy though, because we know, so we can say but a square with sides of L so bigger sides than this square that we just talked about. Well, we know that that has a perimeter 4L and a greater area than this square that was supposed to have the same area as the rectangle. So, has a greater area than the rectangle. So this is a contradiction. Because the rectangle was supposed to have the greater area than the square with the same perimeter. So this is a contradiction which therefore proves that squares must have the greatest area of all rectangles of a given perimeter. Now, as I say, I do think that's quite a tricky one to wrap your head around. Go away, think about it, it will make more sense if you have a little think. So, that's it for this paper, guys. Hope you found it useful. Good luck in your exams, take it easy, take care.